So it's recording. Now let's share screens. Let's go here and let's start here. Oh, I meant to put a picture here and I forgot. That's so disappointing. Oh, that's so disappointing. Well, this is the unit is applications of forces. Oh, that bothers me. This is probably going to be the last time I teach this course in a while. And I've got some dumb parrot instead of a cool applications of forces thing. I'll have to fix this. Oh, well. Anyways, we have 5 lessons, which means today, and then what's tomorrow? Thursday. So then tomorrow, and then 3 next week, and then kind of 1 day of study, and then we'll come back to a test. We'll talk about this tomorrow or next week in person, because oh, you know what? It wouldn't be so bad because Monday would be a kind of a remote day, so that'll kind of get you used to it again a little bit, because it would suck to walk into the building after break and walk into a test. But if there's a day, on either side, that'll probably help. All right, good talk. I'm just talking to myself. I'm going to assume. Let me just see how many people are here. You know what? I'm just going to need verbal, because when I'm trying to see the screen, trying to see like who's all here, and I'm trying to see kind of the notes and stuff. So if you don't get the notes, if I'm going too fast, please say something. I won't be able to rely on a little kind of thumbs up emoji stuff. Anyways, I'll shut up so you can take this down and I'll talk about it. Room temperature Gatorade flavored club soda. This isn't the life, then I don't know what is. Well, you know what? I think I've got an idea here. When you're done with the notes, give me the thumbs up on the screen. I think I can figure out how to do this without blocking anybody on the recording. So give me a thumbs up when you're done, please. Thank you, Ryan. Thank you, Kate. Thank you, Matthew. Just waiting on you, Mr. True Run. No pressure. Nathan, you still writing, buddy?
Yeah, I'm on the last line.
Okay, sorry, I won't pressure you. Thank you, sir. Gravity is stronger near the center of the Earth. Weaker on Mount Everest, you won't notice it. Now, it says it's weaker at the equator versus the poles. Anybody know why? The equator, around the equator, is further away from the center of the Earth than the poles are. The Earth is not a perfect sphere. It's an oblate spheroid, which means it's kind of like, you know, if you have a beach ball that's full of air and then you press down on the top, it kind of bulges in the middle and gets flat on the top and bottom. That's kind of the shape of the Earth. It's a non-contact force. Gravity is a property of everything that has mass. That's why you're heavier on bigger planets, or the sun, for example. The sun would have, I don't know what it is, would have an insane gravitational pull. Everything has it. The watch on my wrist has a gravitational pull. It's just so tiny, I never notice. Yeah, I think that's the important stuff there. Next one. Whoosh. Oh, I'm gonna move stuff around again. Again, please give me the, oh, that's neat. Give me the thumbs up when you're done with the notes, please. Oh my goodness, how did I do this? I have class. You can talk if, as long as it's other people can hear. They're just writing notes right now, or I can come up there if you want.
I was just wondering, could you give me a rough estimate of Jack's height?
He's tall.
Is he as tall as, who's the tall kid? There was a real tall kid.
Oh, Gavin is tallest. And then Josh Hofer is quite tall too. Jack might be 6'2"-ish.
Okay. I was just gonna send it in. I can always change it.
Right.
Once it's just that we've changed our date because the original reservation shows June 25th, and now we've upped it to May 31st. So I want to get it in so that they're aware that we're.
I'm staring at the top of your head because I think Maya is probably about your height.
Yeah.
And then Adam's probably a couple inches shorter, I'm guessing though.
I'm just thinking of the times that I've passed him in the hallway. I put him at just a little bit above my height.
Oh, is he?
Yeah.
Okay.
But I could be wrong.
Well, it's funny, I wonder if there's something psychological to that, because these kids, when they're lining up, I'm like, oh, you're taller than me. Oh, you're taller than me. How come all these people are taller than me, you know?
Mm-hmm.
But because I was kind of surprised to see him in the hall. It's like, yeah, I'm taller than that kid. No, I'm not.
Yeah, I was thinking Adam's about my height.
Okay.
So I put him at about 5'4", 5'5".
He should be here tomorrow. Same with Maya, if she's
Yeah.
feeling better and she had a cold or something.
Yeah, I can always change it. That's okay.
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 Yep. All right. It looks like I got all the thumbs up. Here, I have a silly. Oh, you guys won't know this answer. Somehow the orientation changed for my little windows, and I don't know how to change it. Anyway, mass versus weight. Mass is the amount of matter in an object that's measured in kilograms. Weight is the measure of the force of gravity. We often use those interchangeably, but we shouldn't. Weight, measure of force, so weight should be in newtons. Okay, weight is a vector because it's newtons. Mass is not. Mass is kilograms. Your weight doesn't change. Your weight changes from here to the moon. Your mass doesn't. If you're on Saturn, your weight is way higher. Your mass does not change. etc. Stop me if you have questions, just giving you the little bits of stuff. Next one, air resistance and free fall. Oh my goodness, it's going to drive me crazy, this little window. Give me thumbs up again when you're all done, please. Sorry, Nathan, I have ADD. I was looking around and then I saw a thumb just disappear. Did you have it up and disappear or you're still writing?
No, I just finished just now.
Okay, cool. So air resistance is friction caused by the air. When I'm talking about cross sections and stuff, I showed you guys that video about with the bowling ball and the feather in the vacuum, correct?
Yeah.
Anyone? Yep. Okay, cool. All right, so you kind of see how that works, which is just really wild to me. Consider figures 2 and 3. I think they're pretty cool, pretty important. I added a little asterisk to number 3 because I often have a test question that deals with that. So here's your little reminder. Now, where are we? Are we here? Yes, we are. Now we're here. Thank you. There you go. I'm just staring at the screen now. I can't promise I'll keep my focus. I'll probably get distracted by anything. Thank you. Beautiful. Immerse the buckets. All right, I'm gonna stop sharing the screen. I'm gonna do some examples for you for page 166. For some reason, I've pinned Nathan, but I don't need to do that. Full screen. All right, here we go. Cursor out of the way. All right, so practice page 166. Number one, it says a 12 kilogram box sits on top of a 38 kilogram box. Draw a free body diagram for each box. So we've got a 12 kilogram box and a 38 kilogram box. Doesn't want a system diagram, wants a free body diagram. So for each box, the 12 kilogram box, I'll just put the 12 in here. You don't need to, but I'm just doing it to differentiate. It's going to have the force of gravity on it. Need the vector on top, and that's it. There's nothing. Oh, what do you mean that's it? There's a normal force. Otherwise, it'd be in free fall. There's a force of gravity, and then the normal force, which is a little bit different from the 38 kilogram box. 38 kilogram box will still have the normal force because it's sitting on a shelf or something, I assume. But it's got the force of gravity pulling it down, as well as the applied force of the other box, because the 12 kilogram box is sitting on top of the 38 kilogram box. So gravity is pulling on this. Gravity is pulling, the 12 kilogram box is pushing. Is that all cool in the gang? I'm going to assume you will stop me if something doesn't make sense or if I'm going too fast. B, calculate the normal force acting on the 12 kilogram box. So the 12 kilogram box, for all intents and purposes, you can treat it just like as if it's sitting on the floor. This one doesn't have any impact on this, outside of that it's between this box and the floor or the center of the earth for that matter. So the normal force, F equals mg. So F equals 12 is the mass, gravitational acceleration is 9.8. So 12 times 9.8 is 117.6, so it's 120 newtons. And it is normal force, so it's pushing up. We figured out, now what I did here is mass times gravity. I figured out the gravitational force. Normal force has to be exactly the same because it's balanced. It's not moving, it's at rest. Cool in the gang? C, calculate the normal force acting on the 38 kilogram box. Well, this one has both masses. So F equals 12 plus 38 times 9.8. So that's 50 times 9.8. It's 490 newtons up. Some of you, I don't know if it's anybody in the room right now, but I'm just about done marking the tests, and some of you are forgetting a handful of, not even a handful, I think maybe two kids are forgetting the direction with forces. That's very important. That's part of the units. Okay, very important. Any questions on number one? If you guys are giving me thumbs up or thumbs down or hands, I can't see it. I've minimized everything, so I just have the screen. So please speak up if something's not right. Assuming everything's good for now. Numero 20 says a child has a mass of 36 kilograms. So the mass of the child equals 36. And is sitting on a seat on an amusement park ride. The ride makes the seat move up and down. Determine the normal force acting on the child when the child is, and then it goes on to do some stuff. So the mass is 36. So we're going to figure out the gravitational force, because assuming the kid is not falling through the seat or flying off the seat, the normal force is going to be equal and opposite to the gravitational force. So for part A, it says moving up at a constant velocity of 12 meters per second. I'm going to write 12 meters per second because we often get thrown when we're given some velocity. It's a constant velocity. Constant velocity means acceleration equals 0. If acceleration equals 0, that means that nothing is going to change the force that this kid feels. So it's F equals mg. F equals 36 times 9.8. 353, so 350 newtons. Running out of page. 350 newtons up. Part B, moving down 14 meters per second, but 14 meters per second is a constant velocity. So the answer doesn't change. It's 350 newtons up. As long as it is a constant velocity, this kid could be going at the speed of light consistently, and the normal force won't change. Although it probably will, because they'll be out of the stratosphere and they'll be further from the center of the earth. But you get the point, hopefully. As long as the velocity is constant, it doesn't change. Which brings us to, I'm assuming it's going to change now, part C. Oh, there we go. Accelerating down at 1.8 meters per second squared. So the ride is going down at 1.8 meters per second squared. So I want you to think about this. I think someone was in my office yesterday and we were talking about kind of how this works. If it's going down at this acceleration, that means it's doing some of the work of gravity. If you're going up, you're resisting gravity. So the force you're going to feel is stronger. If you're in an elevator, and it goes up really quickly, it accelerates quickly, you're going to feel it kind of push into your feet harder. It's going to feel like you're being pulled into the floor. If you're in an elevator and it goes down, accelerating really quickly, it's going to feel like you're lighter. The floor is moving away from you. And that's what's happening here. The seat is moving away from this kid's butt. Is he sitting in the ride? Yeah. So they'll feel a little bit lighter. Gravity equals 9.8. So basically the net acceleration is going to be 9.8 minus 1.8. So it's going to be 8.0 meters per second squared down. So F equals ma, which equals mass is 36, 36 times 8. 288, so 290 newtons up. Normal force? Yeah. Does that make sense? I know it tricks people. Sometimes people have to stop and think, wait, going up means this, going down. Think of you being in an elevator. If it's going up quick, you're going to feel heavier in the seat or on your feet. If it's going down quick, you'll feel lighter, feel like you're floating a little bit. I remember hospital elevators, maybe I'm just used to it now, but as a kid, they seemed to go really fast. And when it would drop, I'd feel my stomach kind of rise up. Nobody's saying anything, so I'm assuming everybody's okay. Number 3. A 72 kilogram person, so mass equals 72. Kilogram person jumps up off a bathroom scale. Determine the acceleration of the person when the scale reads 840 newtons. F equals 840 newtons. Okay, the way I like to explain things is, so generally, if at all possible, not to just kind of memorize. I want you to understand, so you're kind of ready for all situations. The scale is reading 840 newtons. So imagine your scale doesn't say kilograms or pounds, it says newtons. F equals mg. If the force is 840, the mass is 72, then we're going to solve for A. we're going to solve for that acceleration. So 840 divided by 72 is 11.6 repeating. So the acceleration is 11.6 repeating. Now I'm just going to pause here. What do we do? How do we figure this out? Regular person standing on the scale, the acceleration should be 9.8. They're jumping off, so they're pushing down, launching themselves. What do we do?
Take away the acceleration of gravity.
Yeah, exactly. So 11.6 minus 9.8 is 1.9 meters per second squared up, because this is the acceleration this person is jumping with. Anybody having difficulty with that? Cool in the gang? Can I take this away? Is anybody still writing? Last question, numero cuatro. An electrician holds a 3.2 kilogram chandelier, so the mass of the chandelier is 3.2 kilograms against the ceiling with a force of 53 newtons up. So the applied force is 53 newtons and it's up. What is the normal force exerted by the ceiling on the chandelier? If you guys remember when I was talking about normal force, it's not always just a flat surface that you stand on or that something is resting on. It's a perpendicular force from a surface. So there's a couple things we have to think about here. If you want to kind of see like a free body diagram. So there is an applied force of 53 newtons up. You instantly might want to say, well, then the ceiling is pushing down with 53 newtons, but that's not true. Oh, I'm lagging for Kate. Okay. This is being recorded, so it should be fine to look at after. When I get to the end, I'll stop and see if there's gaps. And please, like, feel free to interrupt, or if you want me to stop for a second, I can. I'm in no rush. So what I was saying is, so this person is pushing the chandelier up with 53 newtons. The ceiling isn't necessarily pushing down with 53 newtons because gravity is already doing some work. If we want to find the force of gravity, that's F equals mg. The mass of the chandelier is 3.2. Gravity is 9.8. The force of gravity, 31.36. 31.36. That's the force of gravity. So this is countering the 53 newtons. So the net force that the person, electrician, is the difference between 53 and 31.36, which means that's what the ceiling is doing. So the normal force is going to be 53 minus 31.36. which is 21.64, which is 22 newtons down. How are we doing with that? If you're good and everything makes sense, you can check out, and then I'll know everything's good. And then people just all of a sudden just disappear. If you have questions, I would love to answer them for you. Kate, did you get it all? Did it make sense?
Sort of. I have some questions about pre-cal.
Sure. Okay, so tell you what, let me stop this recording and then we'll go to pre-cal, yeah?
Okay.
Did you have any questions about this?
No, I
Okay.
think it makes sense.
Uh,